Hi, everyone. Thank you for coming and attending our talk. We're going to talk about container security and how we can reduce the attack surface of containers and go beyond the standard namespace isolation. So this is a joint work between Accenture Lab and Stony Brook University. And these are the people that contributed to this work. There's myself, there's Jay, who's present here, Lei. We're all part of Accenture. Accenture is a consulting company, but they also do research, so we're part of the tech lab of Accenture. In a past life, I used to work on mobile security. I worked on car security assessment and also cloud and binary security under DARPA and IARPA-funded projects. And Lei used to work on document classification, machine learning. And Michalis is an assistant professor at Stony Brook University in the computer science department, working on system security. And in a past life, we used to work together in these research-funded programs. And I'll let Jay introduce himself.
Hi, everyone. My name is Jay. Currently, I'm working in the container attack surface reduction project with Azadin. And previously, I've worked on the blockchain security and industrial control system security.
So I assume if you're in the audience, you probably want to know about container and you know already about it. If you don't, I have a container 101, which we'll go over quickly. If you already know, I apologize. And if you don't know anything about VMs, I don't have a 101 for VMs. But basically, the main difference here between virtual machines and containers is virtual machines can be thought of as a completely different system where the instruction gets translated by a hypervisor and they have their own kernel. The downside is that they're very heavyweight, they require a lot of resources. On the other end of the spectrum, you have containers. They're more lightweight. And Docker is the most famous one, but under the hood, there's LXC, there's a bunch of other containerization technology that could be used. The biggest difference here is that you can have a host that shares the kernel with multiple containers. Of course, there's some isolation properties that are handled by the kernel, and it's done through namespace isolation, memory space isolation, and all these things. Why containers, right? What does it actually mean, and what are the advantages of using containers? So this is a great picture that I have not done. I took it from the Microsoft website. That's where you can see the Visual Studio development lifecycle. But I thought it was very abstract enough that it got the point across on how people use containers in CI/CD environment without giving too much details about it. So the way people build containers, and it can vary, right? They can be different instantiation of this workflow. But people build their application, whether it's Java, Python, however you want to build your application, and then they add Docker to it. Once they have added Docker support for their application, and we'll go back on that one after, they run their application, they run their test suites, and that's where the CI/CD loop happens. If the application behaves as expected and passes all the tests in your Jenkins pipeline, then it gets pushed into production, or it goes back to the developer, and the developer has to make changes to this to the code or the container support. But really, the key problem when people are building containers is in this second step. So the way you add container support to your application is by using a base image. The base image, think about it as your operating system for your container. Once you have this operating system, you can actually build and deploy your application in it. It's a copy and write file system, so every changes that are committed on the file system will make a layer. And then that becomes your image. And then your image gets pushed to your enterprise repository, and that becomes your image. The problem in this loop is that sometimes they build a container, and it has all the dependencies for a specific application, but they overload the container image. They build a lot of other dependencies, so they can just use this image as a drop-in replacement for other application. And sometimes they rely straight on public images, which we'll see after have a lot of vulnerabilities as well. So this is really where the key of the source of the problem is. So now if you think about a couple, right? Let's be even more abstract. You're a couple, you live in a great Mac mansion. I don't, but if you do, that's great. But let's say you have all these windows and you have all these doors. That's a lot of entry point for a burglar, right? You need an alarm system, you need sensors, you need all these things. Unfortunately, that's the state of containers and application today. There is a lot of unnecessary pieces. And we want to debloat this house, I guess, and in that case, the containers. And we want to put you in a tiny house that will suit your need. And if you're probably I need something bigger than that. But let's assume you're happy with this size house and you have only the things you need. Hopefully, by reducing the size of these containers or this house, you'll have less entry point, which means less vulnerabilities. And if there's less code, it's just a numbers game, right? Less code, less bugs, less vulnerability. Ideally, that's the expected outcome. So we had a hunch when we started this research, right? So we were using containers for other purposes, right? Not specifically doing container security research. And we pulled images that were 600 megs, 1 gig, and there's no way you need like 1 gig for MySQL or any other type of application, right? So we decided to look into how people are actually building containers. And if you remember before, this is the step 2 when people add Docker to it. So when you build a container image, you start from a Docker file. On the left-hand side of this picture, you can see the first line from, which is basically you declare your base image. What is going to be the foundation on what this container image is going to rely on? And here you say that basically you want Ubuntu 16 to be your base foundation. Okay. There's no way you need all Ubuntu to run a specific application, right? You should be able to tailor it and trim it down to actually the pieces that are required for this application to run. And then you declare a bunch of environment variables, commands that you run into containers. So you can see the run apt-get. So all of these operations until we reach command will basically be written on committed to the file system, and that will be part of the layer. And on the upper right corner of this picture, these are basically all the layers that composes this container image. And this is really the problem. That's where the problem starts. So we had a hunch, and we decided to look into actually, like everything, when you do research, you need to ask yourself, is it a valid question? Is there work already done in that space? And is there something we can do, right? Can we improve on the situation? So we have actually looked and analyzed some Docker repositories, so that's not the focus of this work, but we literally pulled all the container image across versions since the inception of DockerHub, and we decided to pull some statistics out of it. So on the left-hand side, you can see all of these packages. So these are the top 10 vulnerable packages. Some of them have literally thousands of vulnerability. So what it means is, if you have a lazy developer or not so careful developer that would just pull some images and run them into production, you're going to inherit the cost of managing, fixing, or patching, or containing these vulnerabilities. On the right-hand side, these are the most vulnerable packages that are used currently. It's not as bad as the left-hand side, right? The left-hand side are probably older versions. But if you look on the right-hand side, so these are more recent versions, and you can see that they still have double digits vulnerabilities. So we looked into after that, this is just some other number. And I'm going to just display this picture for a little bit and let it sink in for you. So these are the top, at the time where we conducted our experiment, these are the top 20 Docker images in use on DockerHub. So this means that these are actually probably running somewhere in production. And we did really something very simple, right? We automated the pool of these containers, we deployed them into an environment, and then we assessed the vulnerabilities using Claire, which is an open source scanner. And you can see that some of them have literally triple-digit vulnerabilities, and and we'll see after that the size is pretty big for what it is. But this really means that for us that there was a need and something we knew that we could do something in that space, and really there's a need. Nobody should be managing, maintaining, and paying for these vulnerabilities when you can just get rid of them, or at least the hope is we can get rid of most of them and focus on actually the pieces that we care about. And now I'll hand over to Jay, and he's going to tell you a little bit more in details about how we can address this issue.
Thanks, Asadin. With all the bloating issue that Asadin has mentioned, as a security researcher, we want to develop a solution to mitigate the problem. So we want to debloat this bloating image. The concept of container is that each container should be designed with single purpose. And similar to the philosophy in Unix, each container should only be designed to execute one task and only do one task that it is good at. For example, a container with web server shouldn't be a database, and a container with database shouldn't be a file server. However, a lot of the containers we see today are built more like a virtual machine. Maybe because of the legacy issue, how they convert a virtual machine to a container. A lot of containers actually contain a lot of unnecessary package or components. And when you add these unnecessary components and package into your container image, while they are not doing anything for application, they introduce a lot of vulnerabilities, and thus enlarge the attack surface of the container image. With all this problem, we are proposing a methodology, a two-stage methodology to create a more secure and lightweight container image. In the first stage, we want to profile the normal workload of a container. Once we understand the normal behavior of a container, then we can use the profile to build another smaller container image that contains only the function that this application really needs. So at the end, we will have a smaller container image and hopefully with less vulnerabilities. To profile a container is not too different than profiling a Unix or Linux application. We can do it from either user space or kernel space. However, we prefer to do it in user space because it is not always possible to make change to the kernel space. One way we can do it in user space is using the system call called FetNotify to get a callback for any file system activity, including the file open, file close, or file read or file write. Very simple in user space. And another way we can profile a container is using the library interposition. So library interposition is a very cool technique that allows us to instrument any function in any library. However, before you can instrument any function, you need the prerequisites that you need to know the symbol name of the function. And another concern is if you instrument a function, a very busy function, or if you instrument too many functions at the same time, it can cause a lot of overhead and impact the normal performance, the normal behavior of the original application. And in terms of the networking activities, there are also multiple options that we can tap into. We can monitor the networking activity of a specific container. On the top left-hand side, we can again use library interposition. We can tap into the function, like glibc library in the container itself. And for networking activity, we can tap into the connect, accept, or bind networking related functions to see the networking activities. We can also tap into the networking interface ETH0 or ETH1 directly inside the container or inside the container network namespace. And we can actually run like tools like TCP dump directly in the specific network space. And another option is to actually tap from the host itself. In terms of Docker, they usually create a bridge between the container network namespace and the host network namespace. And we can tap into that bridge on the host directly and see all the traffic between the container and the host. To recap our methodology, we want to find a way to profile a container in user space. We can use either library interposition or leverage the existing system called API to get event notification. And there is a limitation. So in our first phase that we have completed today is that we can profile an application using these techniques. And based on the profile, we can build another debloated, reduced image that can support only the functions observed during the profiling process. However, there's a limitation. Our container is as good as the profiling. If there's anything that we did not observe during the profiling process, the debloated, the reduced container will not be able to support those functions. That's why we are aiming for in the second phase, we want to do a continuous monitoring in production and provide a continuous refinement for the debloated image as well. Now I'm going to do a quick demo to show how our container debloating technique can help reduce the attack surface of container. And this is a live demo. I hope it can work. Yeah. This. Okay, this looks better. So the specific container application I'm using today is WordPress. So I'm starting the WordPress application normally, and trying to load the web page. The network is a little bit slow here. And okay, this is a home page, and I'm going to look at the admin site. And one thing I want to point out here is the plugin in the WordPress container now. There are currently 3 plugins, and none of these plugins are actually activated. However, we know there are known vulnerabilities in this plugin. And I'm going to show you that even without this plugin activated, we can still exploit this vulnerability. So in this terminal, I'm going to run a simple command to leverage a vulnerability and upload a script file that allows us to explore the container file system. So now I have successfully uploaded a file. And next, I will try to access this file from here. So this is a script that I just uploaded. And with this script running, basically the attacker can do anything in the container, download, edit, or delete any file. And any command can also be run here. So we see the issue here. And next, I'm going to show you how our debloating methodology can help mitigate the issue. So I'm going to start the container again, but with our profiler running in the background. So I start the container again, refresh. Let me go back to the home page. And what I'm doing now is to simulate a system admin. And suppose there are only few features, few functions that the system admin actually need in the admin side. So trying to log in with a very simple password. And let's assume that all the admin care is to see if there is any update in this website and if there's any post from the guest. And let's assume that all the admin care about this website. And now let's look at what the output, let's terminate the profiler and look at exactly what the profiler has created. So this is one of the output file of the profiler. In this file, it shows all the files that the container has touched. So it started from the Docker entry point where the container starts to the point where the WordPress application actually runs with all the PHP file being accessed. And with this profile, we can now build another reduced or debloated image that hopefully contains less vulnerabilities and with less components in it. So I'm building the image now. Here we go. The image built less than a second ago. I actually want to show the size. OK, here we go. The size is 89.1 megabyte. It's called WordPress redu reduced version, comparing to the original WordPress container, which is 407 megabyte. We have approximately 80% of the size reduction. And now let me try to run this reduced version to see if the intended function still works. Let me go back to the home page. A little bit slow, but loaded successfully. Log in. So the admin page is still there. And let me see if I can still check the update. Yes. And let me check if I can still read the post. Yes. But now let me try to do some abnormal behavior. If I want to activate one of the plugins, it is not working because we have removed the function needed by this link. Or if we check the users, no longer available. And I'm going to show, let's try the same exploit again. The result is 44 not found. This is because during our debloating process, the vulnerable PHP file has been removed. Finally, I'm going to show a comparison of the vulnerability before and after our debloating process. So there are 188 known vulnerabilities in the WordPress container. And after the debloating process, we have 0 number of vulnerability. Don't be too excited. This is too good to be true. And there's no way we can remove 100% of the vulnerability. The reason is that during our debloating process, we also remove some of the components required by the vulnerability scanner to identify the installed package and the vulnerabilities. So that's what happened. We are not saying that we can remove 100% of the vulnerabilities. And with that, I'm giving back to Azadin to talk more about the detail.
OK, so a cat must have died somewhere because our demo worked. So somebody made a sacrifice. That's good. Thank you. Now, if you guys remember what we said before about our top 20 Docker images, we actually applied the same method. The graph is not as ugly as it is here as it is on my screen, but you'll have to trust me on that. So basically here, we took the top 20 Docker images that we've had before, and we've run them through our debloating process. And here are the results. So I'm just going to give you a couple of highlights. So the light blue bar, annotated at the top, it's the original size of the container. If you look at the green bars, this is the reduced size. This is after we've processed them. And you can see there's a significant size difference. And then the dark blue bars are the original vulnerabilities. And then the red bar, which you cannot see because there's 0, are the reduced vulnerabilities, right? So I'm not telling you snake oils, right? It is not possible to achieve 0 vulnerabilities. And now we're going to expand onto why this is happening. But across the board, we've observed an average size reduction anywhere between 60 and 90%, depending on the application. And we've observed by our own test, right, about same thing, 60 to 80% of vulnerability reduction. Not 100%, but it's still a decent amount. Now let me explain you why we have 0 vulnerabilities and why if you run that at home, you probably are going to end up having 0 vulnerabilities as well. So if you guys are not familiar with OVAL definition, so it's just a way some Unix or Linux distributions are sharing information about the CVE, the severity, the package name, and which version of package or packages are affected by a certain CVE. And this is what, and this is how vulnerability scanners are working. Most of them, they rely on some information about the Linux distribution or the package manager that handles it. So if you use Ubuntu or Debian, it's apt. If you use CentOS, it's Yum. And then it tries to cross-check, and you'll see by cross-check, it's very shallow what they're doing. They try to identify what you have installed on your system with what is actually present in these OVAL definitions. And sometimes it is as shaky as a regular expression, right? So they tokenize the entry into the package manager list of files that are installed. They extract the package version, the name, and then based on that, they match it with an OVAL definition. Okay, it doesn't take a genius to understand that these kind of tests are not very accurate. Because if you've installed something outside of your package manager, it's not going to be listed there. If you change the file, or if you don't have the same file that is described in the OVAL definition, again, it's going to fail. So again, I think this is a research topic on its own, but we did our best effort, and we actually tried a lot of leading security container vulnerability solutions. I'm not going to mention any names, but I'm sure you've used them if you use containers. But really, what these tools are creating today is a false sense of security, right? You try, you test, you assume that your image is clean or clean enough to be run in production. But the reality is you cannot really trust these tools. And these are just some of the examples, right? If for some reason, they don't work with Fedora or SUSE package manager. They just can't detect some vulnerabilities. And when I say most, it's really most. Not all of them, but close enough. And if you have malware into your image, right, you'd think they would pull some hash from VirusTotal or something to assess them. No, they don't. They really just rely on package manager and OVAL definitions. And now let me tell you how you can be a talented hacker in the world of containers. Just change the file name. All of them do not detect it. Seriously, I'm not kidding. It is that sad. But basically, this is the problem, right? The way these container testing tools are working is very simple and naive, and there's a lot of ways to bypass them. I'm sure the bad guys figured that out too. So we presented you a solution, right, where we actually look at the application running within a container, identify the components that are required for this application to perform, and strip down the rest, right? And if you're in higher functions, I guess, and you're close to the corporate overlord, you can see how it is a problem, right? So our corporate overlord were like, there's no way we cannot change the containers, you cannot change the structure, and everything that is hash-based is going to be an issue, so you need to find something that actually works for us. So what we did is, okay, instead of removing everything, if you know that all the things that are required, you can just generate a whitelisting policy, and that's a way, it's a cheap way to contain the vulnerabilities because they cannot be exploited because you have a policy that denies access to these functions. And I'm sure you're aware of mandatory access controls, right? So the only problem, right, is when you do, if you guys have tried to write a SE Linux policy or AppArmor, you can see that there's a lot of issues with the special files, right? Proc, if you want to read some kernel exposed information in user space, that is an issue. How to write policies, it's a little bit tricky. There's a runtime overhead. The more rules you have, and if you write them naively, by naively I mean if you have a rule that applies to each file instead of having a rule that applies to the directory and the subcomponents, that also generates a lot of overhead. So there's some tweaks and optimization that you can do, but the bright side is you really have fine-grained control on the operations that run within your container. You can, whitelist file, and we'll show an example. You can grant capabilities. And also, your corporate overlords are happy because the containers hasn't been touched, the hashes are the same, and you've maintained the integrity of whatever container image you were working on. And this is just a a recap of the type of permissions that you could enforce with Mac. And the interesting one is the capabilities, right? You can limit also the capabilities that you offer to an application. And today we feel really lucky because we're going to try again another live demo, and hopefully it doesn't fail.
So I'm going to run the very similar demo again, but with the only difference is that this time we will use the mandatory access control policy to secure a container instead of actually remove the component inside the container. We will still run the same container, but instead using the same profile, we will generate a set of policy to limit the file access permission inside the container. So I'm again starting the container with the profiler running in the background, and I'm going to simulate the normal user activities again. Let me first log out. And log in again. And I'm going to perform the same two functions that the system admin supposed only need. Check the update, check if there's any security update, and check the latest post from the guest. And log out. That's it. Suppose these are the only two functions that the system admin need. And I'm going to terminate the application and the profiler and show you exactly how the profile looks this time. So again, this is one of the profile that generate based on the file system activity. This time we collect a little bit more information. We also collect the file permission and also the type of access. Previously, when we deploy in a container, a file is either available or not. But this time, when all the files are available, but we can actually provide more granular control to each specific file. We can specify if this file has read access, write access, executable access, memory allocation, or linkable access. So with policy, we can create more granular control to each file. And with this profile, we can generate a set of policy that I will show you next. So this is basically the policy that whitelist the files in the WordPress container, and this policy basically will only allow the function that we observe during the profiling process. Now let's run the same container application again with this policy deployed in the kernel. Load the home page, and let me log in. And let's see if the intended function still work. Check the update, check the post, and let's see if we can do any user, check any user. No, the page is not available, and this time we get a slightly different error message. Instead of saying for not available, this time we get a permission denied, because the file is still there, but we've simply enforced the policy to deny the access to this specific file. And similarly, if I try to pull the same attack, the same exploit again, unsuccessful, and we get a different error message, failed to open stream permission denied. Again, the file is still there, but our policy, this file simply is not in our whitelist. Okay, let me get back to Azadin.
Okay. So we've just shown you a demo, right? Two demos. The first one is, think about it. You're running an application and you have dependencies. In that case, that was plugins, but that could be, libraries sitting on your system, shared objects that are completely unnecessary for your business purpose or your application purpose. Yet you're still exposed to a lot of vulnerabilities and potential compromise for something you actually didn't need. And we showed that removing all the things that are not, whether it's components, whether it's files, we removed all the things that were not used by the application. You actually reduce the attack surface, you reduce the number of vulnerabilities, and as a bright side, downside, you reduce the size of your containers. But this is really coarse-grained operations, right? We're removing binaries. By binaries, I mean ELF files or exe if you're using Windows. But what happens when we actually, when you actually need to run this application, but the vulnerabilities are still within the application itself? And let's assume you also don't get to the source code. So this is the application layer. And I put this little surgeon picture because this is really like surgery, and it's more fine-grained than working with the containers themselves. And if you think about if you think about containers and application today, there's a lot of bloats, and I like to think of them as being very fat. Containers, applications. There's really a lot of things you don't need, right? These applications today, like, I don't know, I think Facebook is 400 meg on iOS or something. It's ridiculous, right? You don't need that much for a web-based application. That's another story. Anyway, there's always going to be bugs, right, in application. And if you look today, the leading cause of system compromise is bugs. Bugs gets exploited through buffer overflows and rob gadgets and all of these good things. And of course, there's a lot of initiative in that space, Patch Tuesdays and updating your system and package manager to make sure that you have the latest and greatest versions. But really, it's not enough because the attackers might find before you patch the application. And of course, if you look through history, right, through smashing the stacks, return to libc, and rob gadgets, the technology evolved. And there's a lot of mitigation strategies that are applied and that are working very well and put the script kiddies at bay, but there's still talented people that can exploit the application. And in terms of attacks, right, there's application that simply overwrite a return address and you can return to libc and execute, you prep the stack and you return to certain functions that you care about. There's slightly, and of course, in that case, you can target functions that are not used by the application. Or even better, if you guys are not familiar with return-oriented programming, it's basically a way to leverage the code that resides within the application binary. So you disassemble your application. You have a bunch of basic blocks. Basic blocks are basically something that finish with a return instruction that allows you to set the stack and call arbitrary functions and set the stack in a proper way so that you can pass the arguments you care about. And of course, same thing as before, there's techniques, right? Address space randomization, there's control flow integrity, there's shadow stacks. There's a lot of techniques, right, in the defensive sides. There's also a lot of talented people that can bypass these techniques. So if you think about what we did before, why don't we apply the same concepts to an application? It sounds intuitive, right? You take the application, you look at the functions that are used, and you simply strip them out. I said simply because binary is a little bit tricky, right? There's a lot of offsets and things that you need to care about if you do it statically. But if you do it at runtime, think about it. You load the library in the address space of the process. You can null some memory pages that contains the function you don't care about. And if the exploits are actually leveraging functions that the application doesn't use, then the application, the exploit will break. But this is all type of attacks. These days, it's more, all the hype is around return-oriented programming and gadgets, right? So this type of attacks will still succeed even if you remove the functions that are not used by the application. And there was some work that was done previously to remove these functions. So that's if you think about the level of granularity, that's lower than what we presented before, but that was code stripping. And code stripping says the same thing. It basically removed this function, these symbols, from the address space of the process. Here, what we're doing is we're looking at gadgets and the way they're built. They only leverage a couple of critical functions. So these functions are still required by the application to perform, so code stripping is not going to work. So what we're doing is we enforce something at the API level. API, I mean, Windows 32 APIs. And so this is the case that this is something that we call API specialization. And the threat model is we assume that they have full function reuse, they can do everything, and our main goal here is to really restrict how the API will interact with the operating system. And if you think about virtual alloc or mprotect or malloc if you're using Linux, we really want to enforce how these APIs are used and make sure that an attacker, because the attacker side is using the same functions but with different argument, right? You may allocate a memory page and mark it as readable, but the attacker will use the same memory page but mark it as writable and executable. So these are the same functions. So code stripping doesn't work. You really need to enforce how these functions are called and the type of arguments that are passed to these functions. And this is, very high-level functions. If you have a Windows binary, so this work was based on Windows. And by the way, I'm channeling my inner Michaelis because that was most of his contribution in that space. So you have an application. Windows application, most of them will map kernel 32 DLL into the address space of the process. And if you look at the bottom on the right side of this picture, we're using only 4 functions, right? But because you're mapping kernel 32 in the address space of the process, you get access of, you and an attacker get potentially access to thousands of functions. But you don't really need all of that. So this is really the case for API specialization that we're making here. And this is a simple study, right? We look at these Windows 32 APIs, or DLLs, however you want to call it, and we looked at the number of functions they have. Kernel 32, of course, being the biggest offender, right, provides a lot of features and support for the Windows application, has 1,900 functions. And then we looked at the application and how many functions were they actually using within these libraries. And you can see that VLC only needed 38 functions out of 1,900. And if you look at ADV API for VLC, they needed only 2 functions. Yet there's 900 functions loaded into the address space of the process. Again, it makes no sense, right? If intuitively you don't need to overload yourself with all these functions when you can strip them down. So what we did is we want to create specialized version of this API and enforce some policy on it. And what we did is we looked into all these APIs and how they're used across ROP chains and exploits, and we've identified 52 what we call security critical API functions, right? Such as virtual, so that's the equivalent of mprotect, malloc, and connect is connect everywhere. And the goal here is we analyze how the application is going to do insert the arguments for these functions, and ideally, and most of the time actually, the malicious application, right, the exploits, are using the same functions but in a different way with different types of argument. And of course, that's the main intuition behind this work, and hopefully that works. But spoiler alert, it does. That's why I'm here. But the idea is that this approach should be we want to work on binary. We don't want to do live profiling as we did before. We want to do something completely statically, because if you're able to observe the argument, then it's not cheating, but it's easier, so to speak. It's a best effort approach. So if we cannot infer the argument statically for a function, we're not going to try to enforce a policy on it. We only enforce the policies of the arguments we're able to identify statically. And then, of course, like any technique, right now it looks great, but maybe tomorrow someone will find a way to bypass it. But that's the game, and that's why there's a conference every year in security. And the idea is that it's lightweight enough, but it also can be alongside other applications. So it's a 2-phase approach. Basically, we take the application binary, we disassemble it, we extract a control flow graph, which enables us to see all the basic blocks, and we identify the call sites for these 52 critical functions that we've identified. Once we have that, we do backward slicing, and we're able to infer the argument on the stack that are pushed to this application, and then we generate a process-wide per function policy, which means that we enforce a certain behavior for specific API calls. And then at runtime, it's your classical library interposition, and we leverage something from Microsoft Research. So what does it look like in practice? So this is basically the same as before, but in picture, in case you don't know how to read or you didn't like my explanations. But basically, we look at the intersection of the critical functions and the imported functions by the application. We identify the call sites, and this is the argument, right? This is ideal scenario. You have all the values that are pushed on the stack prior to invoking the API calls. Of course, many times it is not possible, and we can't infer a policy for specific functions. But every time we can infer these arguments, we're going to enforce it. And some of them will be determined at runtime, and that's fine, as long as we enforce part of these arguments that are called for this API call. So the prototype we have is Windows-based, no secrets, we're using IDA. And the enforcement is done with Detour. So if you guys never used Detour, never heard of it, I'm not sure I don't think it's open source, but it's free to use for academic licenses. And basically what it does is that every time you enter one of the functions you care about, it inserts a trampoline instruction, and then it jumps to your own implementation. So that's a very nice way of doing library interposition on binaries for Windows, because there's no LD preload on Windows, unfortunately. So these are the results. So we took 251 shellcodes and 30 raw payloads that apply to common application. We took 10 what we call popular end user programs, and that you're going to see the names, right? It's zip, VLC, Chrome, and things like that. So it's real world, right? It can actually work. And the main results, as I told you, so it improves slightly for shellcodes, but shellcodes will use functions that are not used by the application, right? So the improvement is minimal here. However, if you look at ROPS chain will use only 1 or 2 critical functions, but it will use it very differently. And it has a very negligible overhead. And this is just a graph of these results. So we used Chrome, Edge, Firefox, and a bunch of other applications. So this is actually working on a real application that you may download today. So we call this API specialization Shredder. So that's a best effort software reduction, attack surface reduction tool. It goes beyond the simple code debloating to API specialization. We really believe that it's fine. You could have multiple instances of kernel 32 DLL. Memory is cheap. We can store many versions of that DLL and load them into the address space of the process. It relies on static analysis, and then the policies are enforced at runtime. So whatever we can infer statically, we do it and we enforce it. And of course, the major improvement is on ROP chains as opposed to shellcodes. So now it's time for me to conclude. So we show multiple approaches to reduce the attack surface, right? We looked first into the coarse grain approach for containers and container image and really removing all the binaries. And then we targeted something a little bit more fine-grained, where we look at the application and what's left of it. And the main takeaway here is that, whatever vendors tell you, whatever solution pitch you read, software solution or security is really a defense in dash solution. There's nothing that fixes everything. I know some people believe appliances will fix everything at the network layer. Some people that sells API solution will tell you just protect your APIs and you're all good. But really, security is a defense in dash solution. And really, all of you guys, whatever you're running today, your attack surface is too big, and your security team is too small, right? So, and if you look at all the techniques, right, incident response and all that, the biggest problem is reducing the noise. With this, you can literally reduce the noise because all the alerts or everything you get is going to be targeted to your particular need and the functions you're actually using. So containers are still good, right? I'm not saying containers are bad in that talk. Containers are great for DevOps, they're great for agility and deployment, but again, the problem is really the sad state of the testing tools today that really gives you that false sense of security. And there's a lot of things you could do, right? And I know, and I'm sure in the room people will say, oh, you can just use Alpine, from the Docker file. Yeah, great. Alpine still has a lot of dependencies that you don't need for your container. And for those of you who don't know, Alpine is just a lighter operating system that contains less bloat than others. But really, containers should be built as a single-purpose tool. And they should only have the things you need for your application. And that's it. If you guys have any questions, I think we have time. No? No, sorry, no, we don't have time. Because we have time.